Well, here is another video, and this time we are looking at the ideal gas equation. This is actually a lab, a simulation lab that gives you an idea of what the ideal gas equation stands for. So PV is equal to nRT. That is the ideal gas equation. Let's look at each term. P is the pressure in pascals. V is the volume, must be in meter cube. N is the number of moles. Now what is that? We'll get to that in a minute, but it's just a number. It has no units. R is a constant for all gases. It is called the universal gas constant, and its value is 8.314 joule per mole Kelvin. T is the absolute temperature. That means it has to be in the Kelvin scale. So those are the terms in the ideal gas equation. Next, we look at the volume of this container used in the simulation. Now it's a container that has a length, a width, and a depth. So it's not exactly a cube. The depth is 4 nanometer, and you know a nanometer is 10 to the negative 9 meters, so it's 4 times 10 to the negative 9 meter. The height is 8.75 nanometer, which is 8.75 times 10 to the negative 9 meter. It's the length that is variable, so the depth and the height are constant. So we don't even see it in the simulation. You only see the length along the x-axis, and that length can be adjusted. By default, the length is 10 nanometer, which is 10 times 10 to the negative 9 meter. So the volume is the product of the length, the depth, and the height. All three are nanometers. So when you have the 10 to the negative 9 multiplied 3 times, you would get 10 to the negative 27. So you see that there, 10 to the negative 27. And then you have 350 when you multiply 4, 8.75, and 10. So that's the volume of this container. It's a very tiny container. In the simulation, it's highly zoomed in, okay? But it's a tiny container. Its volume is only 350 times 10 to the negative 27 meter cube. Now comes the difficult part. We're going to actually use this ideal gas equation, PV is equal to nRT, and try to make some calculations. Okay, number one, we will try to find the number of moles. So we have to know that there is a unit called atomic mass unit, AMU, atomic mass unit, and 1 AMU is 1.66 times 10 to the negative 27 kilogram. Here there are two different types of materials that could be used. The lighter one is helium, and the heavier one is nitrogen. So we're going to use the heavier one, which is nitrogen, and it has a mass of 28. So 28 atomic mass unit. That's the mass of one molecule of nitrogen. So let's get that in kilograms. 28 atomic mass unit should be multiplied with 1.66 times 10 to the negative 27. So you will get it in kilograms. So we get the mass of one molecule of nitrogen, which is 46.48 times 10 to the negative 27 kilogram. In the simulation, we're going to have 200 such molecules. 200 molecules. So the total mass of 200 would be 200 multiplied by this. So you would get the total mass of 200 molecules as 46.48 times 10 to the negative 27 multiplied by 200, which gives 9296 times 10 to the negative 27 kilogram. I know I'm not putting it in the standard or the scientific notation, and there is a reason. You will see that. So that's the total mass of all of the 200 nitrogen molecules. Now we got to find out how many moles that is. So remember that the molecular weight expressed in grams is 1 mole. Since the molecular weight of nitrogen is 28, 28 grams of nitrogen will be 1 mole. 28 grams of nitrogen. That means 0.028 kilograms of nitrogen is 1 mole. So let me write that. 28 grams or 0.028 kilograms of nitrogen makes 1 mole. Therefore, how many moles is this? That's a question now. So 9296 times 10 to the negative 27 kilograms is how many moles? Quite easy. You take that number, divide it by 0.028, and you will get the number of moles. So the number of moles is 33.2 followed by 3 zeros. So that's 332,000 times 10 to the negative 27 moles. It's a small number, remember. It's a tiny container, so it has only that many moles in it. So now we're going to calculate the theoretical pressure in this container. So once again, PV is nRT. We're going to calculate the pressure. So pressure is nRT by the volume. We know the number of moles. We know the gas constant. We're going to keep the temperature at 300 Kelvin. So we know that. We've already calculated the volume of the container. So now we can find the theoretical pressure in this container, which is what we're going to do. The number of moles was 332,000 times 10 to the negative 27 moles. So that's the number of moles we got. The universal gas constant is 8.314 joule per mole Kelvin. We are maintaining the temperature at 112 Kelvin. Oh, did I say 300 Kelvin? It's 112 Kelvin, okay? That was a mistake. So we're keeping the temperature at 112 Kelvin. And the volume of the container is 350 times 10 to the negative 27 meter cube. So the pressure would be N, that's N coming up, or it's 8.314 times T, which is 112, divided by the volume. Just a matter of substituting that and calculating, which gives us 883279.36 pascals. So we get the pressure in pascals. But in the simulation, the pressure, well, you could get it in pascals or you could have it in ATM. So I think I'm using ATM. So to change this into ATM, you divide by 101325 because 1 ATM is 101325 pascals. So when you do that, you get the pressure in the container in pascals. In ATM. So 8.71 ATM is what we get. Now, that's the theoretical pressure. We are going to now look at the experiment, the simulation, and then we will get the experimental pressure and then compare these two values. That is the first part of this lab. Let's do it. Okay, so here is the simulation. See, I'm heating it up so you can see the temperature going up, climbing up to 21, 22, 23, and you can see that the pressure is increasing likewise. So the volume is kept a constant, you see that on the screen. And as the temperature increases, the pressure also increases. And we got to get to 112 Kelvin. There it is, 112 Kelvin. And okay, 112 Kelvin, and the pressure keeps going up. So, the pressure will fluctuate a little bit because the molecules are continuously colliding, moving around. So we got to take the average value of the pressure. You can see it's like 8.6, 8.7 is the average value. So you have to watch that carefully and get the average pressure. Okay, so it's going up from 8.3 to 9. Okay, now I stopped it at 8.8. So That is the pressure that we get, 8.8 atm. So there are three other parts. In the first part, you got to keep the pressure constant. You can see on the screen. The temperature is initially at 300 Kelvin, and then you take the temperature to 250 Kelvin, all right, 250, and you see the pressure is constant at 16.3, but see the volume changing? Right now it's 11.9 nanometer. You only get to see the length changing. And then if you take it 200 Kelvin, you see it's 9.6 nanometer. You actually got to do the simulation, so I'm going to move fast. And then similarly, you move it down to 150 Kelvin, and again the volume decreases. So when the pressure is constant and you decrease the temperature, the volume decreases. So that's the idea. 150 gets 7.2 nanometer. Remember, we are using light particles, 200 light particles, and then at 100 Kelvin, you get, let's get there. Oh, oops, pressure cannot be held constant, volume would be too small. Okay, so the minimum volume is 5 nanometer, so we could only get up to 104 Kelvin. And, well, in this next part, the volume is kept constant. And we're going to look at how the pressure changes when you change the temperature. So 250, you get the pressure to 19.6 something, close to that. Then take it down to, that's at 250, take it down to 200 Kelvin. Pressure is going down. It's fluctuating around 15.7, 15 point, okay? So see, I'm cooling it. So to bring the temperature down, I'm cooling it, and you see how the pressure changes. So let's take it 150 Kelvin. 150 Kelvin, the pressure is again decreasing, fluctuating around 11.5 atm. Okay, at 100 Kelvin, it's a little difficult to adjust it exactly to 100, but you can do it, cool it, one step at a time. There we go, 100 Kelvin, the pressure is 7.8, is it? Yeah, right there, 100 Kelvin. All right, so there we see the change in pressure with temperature when the volume is constant. And finally, we hold the temperature constant and look at how the pressure changes when you change the volume. So you'll have to drag this handle. I brought the volume to 12.5 nanometer. You remember, that's not the volume, but that represents the volume because we're decreasing it proportionately, okay? So temperature is at 300 Kelvin. And now, you know, I'm going to decrease the volume further. There you go. I'm going into 10 nanometer. And there you see the pressure increasing now. As the volume decreases, the pressure is increasing. So they are inversely proportional. You see the relation? So this is Boyle's law, okay? This is Boyle's law. And again, take the volume further down to 5 nanometer, 7.5. It's a little tough there, 7.5. So when you have it at 7.5, you see the pressures again up. It's around 31 atm now. And then finally to 5 nanometer, and you get the pressure very high, 46 atm, right about there, okay? So these are the three. We are holding the pressure constant, so P is a constant. N and R are already constants. So now we have three constants. If you take P to the other side and then pull temperature to the left side, you're going to get volume by temperature is equal to those three constants. So on the right side, all of them are constants, because on the right side, we're going to get NR divided by P. So this is Charles' law. So that is from the first analysis. On the other hand, in the second one, we considered the variation between temperature and pressure, holding the volume constant. The volume was kept at 10 nanometer. And so here, once again, PVs and RT, now volume is constant. So P by T is equal to NR by volume. which are all constant. So the right side, this entire side is a constant, okay? So that means pressure by temperature is a constant. This is GAY-Lussac's law. And that is the graph again. That means as the pressure increases, the temperature also increases. That's what we found. Finally, we came to Boyle's law, where we had volume and pressure with temperature being constant. All right. And this time the graph changes, and you're going to see that from this equation. All three terms on the right side are constant because N and R are constants and we are holding temperature constant. So it's now pressure times volume is a constant. See the difference? So you multiply two numbers and you got to get a constant. That means when one number decreases, the other number has to increase so that their product is the same. So that's what you see here. When you increase the volume, you see that the pressure is decreasing. See that? So that is Boyle's law. So the nature of the graph is different. Boyle's law. So we looked at Charles' law, GAY-Lussac's law, and Boyle's law. And in the beginning, we calculated the theoretical pressure and compared it with the experimental pressure. So there are four activities that you need to do in this lab to give you a better understanding of gas laws. So I hope you understood the gas laws, you understood each term, and I also did a meticulous calculation on the number of moles just to show you how we arrived at that. So hopefully this lab gives you a better idea of gas laws so that when you're asked to solve problems on this, it becomes relatively easy for you if you have watched this video carefully and if you have really paid attention, which is a crucial thing to get a better grade. All right, this is me signing off. We'll see you on the next video quite soon. Thank you.